Today, we're going to discuss orthogonal diagonalization. So let me quickly remind you what diagonalization is. This is what we said on Tuesday. So this is a summary of Tuesday. So let A be an n by n matrix. And to diagonalize the matrix means to factor. You factor this matrix in the following way. You take your matrix and you write it as M, D, M inverse, where D is a diagonal. And we indicated the benefit of this type of factorization is very often has to do with the fact when you want to compute the powers of the matrix. There are all sorts of reasons why one would want to compute the powers of the matrix. I did give you one such instance, but you can probably find more in the book where the solution to some problem requires you to compute powers of the matrix, and this is very convenient for computing powers of the matrix. This kind of factorization is also convenient for other things as well. And let's just summarize how you find this. To find the matrix D, you need to calculate the eigenvalues of the matrix. You find the eigenvalues of the matrix. And then D is going to be the matrix. It's going to be a diagonal matrix that consists of the eigenvalues. And then zeros everywhere else. And how do you find M? And then what you do next is you find the basis. You find the basis of eigenvectors, each eigenvalue. So you need to find the basis of eigenvectors. So you want to find the basis. So you need to find some kind of basis consisting of these eigenvectors, and you want that AXI is going to give you lambda I XI. And then the way you find M is, for M, you can choose the matrix of eigenvectors. So you would just take your vectors and you would arrange them into a matrix like so, as columns, because that's usually how we think of vectors. We think of them as columns if we want to think of it as a matrix. And then that would do it for you. We did make a comment that diagonalization is not always possible. There is something, if the reason why diagonalization is not always possible is because, as we know, sometimes you cannot find an eigenbasis. It may happen that you simply do not have enough eigenvectors. So if some of these eigenvalues are being repeated and the geometric multiplicity of these eigenvalues does not match the algebraic multiplicity of the eigenvalues, then it is not possible to find a basis, in which case you're not able to diagonalize. There's something else you can do. There's something called the Jordan factorization of a matrix, but it's not something we're going to talk about. That's just not a topic that we need to know. If one was to take like a second course in linear algebra, then that's something you might discuss. It's not necessarily possible to write a matrix in diagonal form, but you can get very close, and that's called like the Jordan factorization, as opposed to this type of factorization. But it's not something we're going to talk about. So diagonalization is not always possible. However, if all your eigenvalues are real and distinct, right? So that means they all have algebraic multiplicity equal to 1, then this factorization is possible. Because in that case, you definitely have enough eigenvectors to do that, because for each eigenvalue, and since they're all different, for each eigenvalue, you can find at least one eigenvector. And if you just pick whichever one that is and you arrange them like this in the matrix, then you will get your factorization that you're looking for. Now, what are we talking about today? So today what we're going to be talking about is going to be the same setup as before. So as last class, A will be an n by n matrix. And this time, we want to find the orthogonal diagonalization. What does that mean? It means it's the same thing, but the requirement now is better. You want to write the matrix in this way. So this time what you want to do is you want to factorize the matrix as O, D, O inverse, where D is a diagonal matrix and where O is an orthogonal matrix. Is an orthogonal matrix. And to quickly remind you what it means to be an orthogonal matrix, we did talk about this last week, but just to quickly remind you what that means, an orthogonal matrix has the property that its inverse is the transpose. The idea being that finding the inverse of a matrix is difficult. That's not an easy calculation to do, especially if you have a large matrix, because there's a lot of things you have to row reduce to find the inverse, whereas finding the transpose of the matrix is super easy. You just interchange the rows and the columns. So this is far more computationally easier to do than this. If I give you a 100 by 100 matrix and I ask you to find its inverse, you're going to take probably many days or many weeks or many months finding its inverse. But if I ask you to find the transpose of the matrix, you can probably just do that in a few minutes. It's still going to be a little bit tedious because you have to carefully line up the rows and columns, but you would be able to find the transpose very quickly. So what this implies is that you can also write it like this. You can also say that A is equal to the orthogonal matrix times the transpose of the orthogonal matrix, because orthogonal means the inverse is the transpose. So that's the other way you can do it. And what you will notice is, so the question is, how can you do this? Can this be done? And in fact, you will see that the steps for doing it will almost be these steps that we currently have. It will almost be the same kind of method, but there's a few things that we have to say first, and then we'll do an example. So let's begin by asking this question. So we mentioned that not all matrices, again, we're talking about square matrices, can be diagonalized. And since orthogonal diagonalization is a better type of diagonalization, because orthogonal diagonalization is, after all, diagonalization. It's just diagonalization with an orthogonal matrix. It's like an even better type of diagonalization. So since orthogonal diagonalization is a better type of diagonalization, clearly not all matrices can be orthogonally diagonalized. In fact, if A has an orthogonal you can say an orthogonal diagonalization. You can also say an orthogonal decomposition. Sometimes you say that. Or you can say an orthogonal factorization. It's all the same. It's just interchangeable words. It just sounds better to say an orthogonal decomposition when you use it like this in a sentence. Then A must be symmetric. Actually, very easy to show. So let's state this as a proposition. If A can be factored orthogonally, then it must be symmetric. So the matrix is forced to be symmetric. And let's give a proof of this. It's actually quite easy to prove. So we're saying if A can be factored orthogonally, it means we can write it like this. O D O transpose, where O is an orthogonal matrix. So we want to show that A is symmetric. So is A symmetric? So is A symmetric? So how do you check if a matrix is symmetric? You have to check. This is what you have to check. You have to check if the transpose is the same thing as the original matrix. That's what it means to have symmetry, that if you interchange the rows and the columns, the matrix does not change. So let's actually do that. So if you do A transpose, that would be equal to the transpose of ODO transpose, because you are taking the transpose of this. Now, we learned somewhere in this course, it's quite a while ago, that if you take a transpose of a product, it is the product of the transposes in reverse order. So I think you actually had that as a homework problem, that this would be the O transpose transpose, this would be D transpose, and that would be O transpose. So you're just writing the factors with a transpose on top of them in reverse order. Now, when you take the transpose of the transpose, that's the same thing as getting back to the original matrix. A diagonal matrix, because all of the numbers are on the diagonal, when you transpose a diagonal matrix, it does not change. And this is just O transpose. So this will give us, if we do that, that will give us that this is O D O transpose. Because again, the transpose of a diagonal matrix is itself. But what is this? This is what we started with. That is just A. That is equal to A. You're just taking this and you're just copy and pasting it in there. And so you have that A transpose is equal to itself. So what this shows is that if a matrix can be factored orthogonally, then it means the matrix is forced to be symmetric. That is automatically forced on you. So that's the limitation, that not all matrices can be factorized orthogonally. They must be symmetric. So the reasonable question to ask now is, what if the matrix is symmetric? Does this work? What if a matrix is symmetric? What if A is a symmetric matrix? Does this always work? And the good news is, you see, when you're talking about ordinary diagonalization, when you're not talking about orthogonal diagonalization, but just ordinary diagonalization, you're just talking about a general square matrix. A general square matrix cannot be necessarily diagonalized. But if you have a symmetric matrix, if you have that extra condition, then not only could it be diagonalized, but it could actually be diagonalized orthogonally. So the answer is yes. The answer is yes. And it has a name to it. So it's called the spectral theorem. You can say that this is probably one of the main theorems in all of linear algebra. This is a theorem. This is called the spectral theorem. And I'm going to give you two versions. This is the matrix version, and then I'm going to give you the linear map version, because we understand that whether you talk in the language of matrices or whether you talk in the language of linear maps, you really are saying sort of the same thing. So I'll give you the matrix version of that. So the spectral theorem says that if A is a symmetric matrix, then it can be orthogonally diagonalized. Always, right? Always. You can always do that no matter what. But that always works. And then the spectral theorem, this is the linear map version. This is like the more sophisticated abstract version, though they really are saying the same thing, would say that if you have a linear map, okay, so if you have a linear map from Rn to Rn, so your linear map is this, f of x is equal to ax, and it says that if A is symmetric, so in other words, i.e., if the matrix that represents the linear map is symmetric, then the linear map F has what is known as an orthonormal basis of eigenvectors. Orthonormal basis of eigenvectors. So it says that you can find the basis B. Actually, there was a homework problem on what it means to be an orthonormal basis, so you can look at that problem again. But it says that you can find an orthonormal basis so that each xi is an eigenvector. And so what does it mean to be orthonormal? That means if you take any two vectors, xi and xj, and you take their dot product, it would be 0 if I and j are different. So any two vectors have 0 dot product, and it's 1 if I and j have the same. And the length of every vector is 1. So basically what that means is you can find the basis of eigenvectors that gives you a cube, pretty much. So this is like x1, maybe this is x2, maybe this is x3, and they're pairwise orthogonal to each other, that they give you a cube in n-dimensional space, like a unit cube in n-dimensional space, because pairwise they are orthogonal to each other, and the length of every single one of them is equal to 1. That's what this is basically saying. We'll get back to this again. I just want to focus on the matrix version, but they really are saying the same thing. And I'll show you why this one is also works. It's very similar to this. I want to focus on the matrix version first, and then hopefully we'll have some time to say about the linear map version as well. So what I'll do is I'll prove this in a special case. We will give a proof of this in a special case. The general case of this is not actually much harder, but it's just going to take up a lot of class time. And in the process of the proof, you will see how to find such a factorization. So we're not just doing a proof just to show you why it works. The point of the proof is also to show you how you find this factorization, because there is a question about how do you actually find these factors. And what we'll do is, as we discuss why this works, you will get to see how exactly these two matrices are found, how the O matrix is found and how the D matrix is found. And then you will see exactly how to calculate that for a specific example. And then after that, we'll do an example. Now, I did not tell you what the special case is, but when we reach it, I'll inform you what's the assumption we're going to be making. So I'll take this down off the screen, and then I'll mention two important facts about symmetric matrices, and then from there we'll be able to justify why this always works. Now, I should say something about complex numbers first. Well, a complex number is a number where you use the imaginary unit. So that means it's a number of the form a plus ib, where a and b are real numbers, and I is the imaginary unit. That means it's the number with the property that it squares to -1. That's what we call the imaginary unit. And that's what we call a complex number. So what we need to know about complex numbers is if we give this a name, if we call this, let's call this alpha. Let's suppose alpha represents the complex number. Then there's something called the conjugate of alpha. That's when you put a bar around it. The conjugate of alpha is equal to, and this is by definition, it's the same complex number, but you replace the imaginary part by the negative of it, and that's what you call the this is called the conjugate of alpha of the complex number. Now, if you multiply something by the conjugate, if you do alpha multiplied by alpha conjugate, let's see what you get. You get that this is a plus ib multiplied by a minus ib, and that's the difference of two squares. So this is a squared minus ib squared, which is a squared minus I squared b squared. But we said that I squared is -1. So if you put -1 in here, you have a squared plus b squared, and you get that this is a squared plus b squared. So it's a sum of two squares. So therefore, if alpha is a complex number, and the notation that you use it is like this, that's the notation for a complex number. That's the notation for a real number. That's the notation for a complex number. So if alpha is something that looks like this, and alpha is not 0, it's not the 0 number, then if you multiply alpha by its conjugate, it has to be something that's positive. It has to be a real number. So not only is this a real number, it is a real positive number. And the reason why it's a real positive number is because it's the sum of two squares. It's a squared plus b squared. If you square two real numbers, they become positive unless there's 0. So if alpha is not 0, then it means these two components, the real and imaginary component, they are both non-zero. Well, they're not both 0 at the same time, and so at least one of them will have to be positive. And so when you multiply a complex number by its conjugate, not only do you get a real number, you get a positive number, a real positive number. Now, another fact that I should say about complex numbers is if alpha and beta are two complex numbers, then you can check. This is very easy to check if you've never seen this before. But if you take two complex numbers and you multiply them and you take their conjugate, that's the same thing as the product of their conjugates. It's the same thing as alpha conjugate and beta conjugate. That's very easy to check. You just simply take alpha, you write it as a plus ib. You take beta and you write it as c plus id. You multiply them, you take the conjugate, and you check that you get the same thing if you do it the other way around. And finally, the other simple fact that I should mention is, so alpha, so this is a complex number, is a real number, if and only if alpha is equal to its own conjugate. Okay, so like for example, if alpha is equal to 5, you would write 5 is equal to 5 plus 0i, and then alpha conjugate would be equal to 5 minus 0i, but that's the same thing as just 5. Okay, so alpha is 5 and its conjugate is 5. So this is a very simple thing to understand, that if you have a complex number and it's equal to its conjugate, if the conjugate does not change the number, then it means the number has to be real. Because, I mean, if you look at this, if you have a plus ib and you replace it by its conjugate, you have a minus ib. If these two are the same number, then it means this b component is the same number. So b and negative b is the same thing. And the only number, the only real number, which is equal to its negative, is 0. And so b had to be 0, so it means the number had to be real to start with. So these are just some very basic facts about complex numbers. I'm sure you've seen this before in your other courses. Maybe you have not really used it that much, so you needed a quick reminder about this, so that's why I did that. But now that we mentioned this, let me go ahead and bring up two important properties of a matrix. So this is going to be proposition 1, and it would say this. So it would say that suppose A is a symmetric matrix, a real matrix. That means the numbers that make up the matrix are real numbers. A is a symmetric matrix. Then all eigenvalues are automatically real. So that is the nice fact here, that if you have a symmetric matrix, then the eigenvalues are automatically real. We saw that sometimes you have matrices, then when you try to find the eigenvalues and you look at the characteristic polynomial, sometimes you're forced to use square roots of negative numbers. So sometimes you have to use complex numbers to find the eigenvalues. But the nice thing about symmetric matrices is that the eigenvalues are automatically real. And let's give a proof of this. And you would think that like this is difficult to prove, but fortunately the proof is very short, and it's a very nice, very simple proof. It takes a few lines. So here's the way we're going to do it. So let lambda be an eigenvalue. Let lambda be an eigenvalue of A. So we want to argue that lambda must be real. Okay? So we need to show that, well, going back to what we just said, we need to show that if you take the conjugate of lambda, you get back to lambda. Right? That's how you show that something is real. If the conjugate of the complex number is itself, then it must be real. So here's the way we do it. So since lambda is an eigenvalue, we can find an eigenvector such that ax, so if you do a multiplied by x, it would be equal to lambda x. But here you have to be a little bit careful. But we need to be a little bit careful since lambda could be complex. I mean, we're basically trying to show that lambda cannot be complex. But since it could be complex, the eigenvector could also be complex, right? So you might be using complex numbers. So in other words, the eigenvector that you're using, it's not necessarily in Rn. It does not necessarily mean that the eigenvector has all of its components be real. Maybe you have to use complex numbers. So maybe the eigenvector is really in Cn. It's going to turn out that's not the case, that it's actually a real eigenvector. But we're going to Right now, we do not know that, right? We're trying to argue that that does not happen. But to be careful, we really have to do it like this. And we will, so we will, uh, so in a moment, we will derive the following equation. And the equation is that lambda, so if you do lambda x dot product x conjugate is going to be the same thing as lambda bar x dot product x conjugate. That's what we're going to show. We're going to show that if that the following equation will have to be satisfied. And so this means this is the conjugate of the vector. So x is a vector. It's an n-dimensional vector, but the components that make up the vector are potentially complex numbers. And this just means you're taking the conjugate of all of the components in the vector. So now when you multiply these two, but the point here is, this is what we were saying earlier. This is going to be a real number. This is a positive real number. And this is also going to be a positive real number. Because if you take a complex number and you multiply it by its conjugate, you get a positive real number, as long as the number is non-zero, which in this case, we know that because it's an eigenvector, so it's not zero. And so we can cancel it away. So we can cancel that number away, since we are not dividing by zero. That's the important part. If you want to cancel something in math, you have to know that it's non-zero. And after canceling it away, we will be left with the following. We will be left with that lambda is equal to a lambda conjugate, right? Because basically what we're saying is you can cancel these two numbers away and you're left with that because they're non-zero numbers. And so, so lambda is real and the argument is complete. So that's basically the way the argument goes. We just have to justify this. Like, why is this true? Like, where does this come from? So let's give a derivation of this. Where exactly is that coming from? So here's where it comes from. We have lambda x times x conjugate. So we can write this as, we can write it like this: lambda x dot product x conjugate. And now, because lambda is an eigenvalue and that's the eigenvector, this is the same thing as ax. So that is the same thing as writing ax. And then you do dot product x conjugate, okay, like that. And now we use this trick that, you see, it's a little bit annoying here because this is matrix multiplication and this is dot multiplication. And it's nice when you have the exact same operation being used. So the way you can write this is, and we saw this before, is you can convert a dot product into matrix multiplication by using transposes. So this is the same thing as ax transpose times x conjugate, which will give us, now open up the transpose. You open up the transpose in reverse order. So that is x transpose A transpose x bar, okay? Which is equal to x transpose A x transpose, okay? Because the matrix is symmetric. That's the whole point. The matrix is symmetric, right? That's the hypothesis that we're making. We have a symmetric matrix. That's where it's being used. It's being used exactly right here, that you can replace A transpose by just A. Now let's keep on going. So this is equal to, so I guess I made a mistake. I said you can prove this in one line. You need 2 lines to prove it because this is really the main calculation. All of this is sort of like the side commentary, but when you look it up in a math book, they usually just write it out. So we need 2 lines to do it. Okay, so now here's what we do next. You can write this as X transpose A conjugate X transpose. Now the reason why you can just put the conjugate over A is because A is a real matrix. It's a matrix consisting of real numbers. So if you put a conjugate over every number in the matrix, you're not changing the matrix. It's the same matrix. Now the reason for writing it like this is because now it's convenient to say that this is equal to X transpose AX conjugate. You could put the conjugate over the product. This is the earlier property that we mentioned, that if you're multiplying 2 numbers together, I know in this case they're not numbers, they're technically 2 matrices, but it's the same idea. If you're multiplying 2 complex numbers together with a conjugate, it's the same thing as multiplying them first and then taking the conjugate. So that's what we're doing over here. But what is AX? AX, X is an eigenvector. So this in turn is equal to X transpose, and then that would be the conjugate of lambda X, okay, which is equal to X transpose, and then we have lambda bar X like this, X bar like that, and then you can factor out, this is equal to, let's just continue. You can factor out the lambda bar because that's just a scalar. You factor it out, and you're left with X transpose X bar, and which is the same thing as taking the dot product between those 2 vectors. So this is the same thing as lambda bar, and you're just doing X dot product X transpose. That's what you're finished with. So look at where we started and look at where we finished. We started with this and we finished with that. And because this is a positive real number and that's a positive real number, it can be canceled away and you're left with that lambda is equal to lambda bar, which means that the eigenvalues are real, right? They can be canceled, that these eigenvectors, well, they're no longer eigenvectors, they're positive real numbers. They can be canceled away, and you're left with lambda must be a positive, it must be it must be a real eigenvalue. So that's one nice property. So this is proposition 1. And now let me mention for you proposition number 2. And I'm going to leave it up to you to prove it because the argument behind this proof is very similar to what we just did. So it's going to be the same setup as before. Suppose A is a symmetric matrix. So let me clear this away. Let's call this proposition 2. Suppose that A is a symmetric, of course, real matrix, and lambda 1 and lambda 2 are 2 distinct eigenvalues. So choose 2. Okay, so we know they must. So we know that they are real, right? We know the eigenvalues are real. So we know they are real. So choose 2 eigenvectors for each of the 2 eigenvalues. In other words, what we're doing is we're saying this. We're saying that lambda 1 and lambda 2, they're not equal to each other, and we're taking 2 different eigenvalues, our eigenvalues. Okay. And you pick 2 eigenvectors. You're going to pick 2 eigenvectors. You're going to So you're going to have x and y. So what does that mean? That means that if you do ax, you're going to get lambda 1x. And if you do ay, you're going to get lambda 2y. So basically, you have two different eigenvalues, and you're picking an eigenvector for one of them, and you're picking an eigenvector for the other one of them. So this is what you have. Then here is the theorem. So the theorem says, then these two eigenvectors are automatically orthogonal. In other words, the dot product between them has to be 0. So it means that if you do x dot product y, it has to be 0 automatically. So if you have the two eigenvectors, their dot product must be 0. I want to give a little caution over here, so just be careful. The fact that two eigenvectors are orthogonal, they have different eigenvalues, is not true in general for non-symmetric matrices. This is a property that symmetric matrices have. It is not a property that matrices in general have. So you do have to be careful with that. And the way you're going to prove this proposition, I'm going to leave this up to you. It's going to be roughly the same proof that we just did. So the details are left for you to derive yourself. And I will give you hints. So here are some hints. So show that if you have to basically show this. You have to show that lambda 1 multiplied by x dot y is the same thing as lambda 2 multiplied by x dot y. So, and the way you show it is by using a similar method. By using a similar method we did in the previous proposition. It's kind of the same thing. Like the way you're going to do it is you're going to absorb lambda into x, and you're going to use the fact that x is an eigen vector, so you can write it as ax, and then you kind of write the dot product with a transpose, and you kind of move things around, and then it works out. So you're going to use a similar method as we did in the previous proposition. And once you show that, then it means that x dot product y must be 0, because otherwise it can be canceled away, and you will be left with lambda 1 is equal to lambda 2, which is a problem. Right? Lambda 1 is equal to lambda 2. Like if the dot product was a non-zero number, like you basically want to cancel this away, right? You want to be able to cancel that away. But before you cancel something away in mathematics, you have to know that you're not dividing by 0. And you cannot cancel it away. If you cancel it away, you get lambda 1 is equal to lambda 2, which is a problem because we said the two eigenvalues are not the same. So that means you cannot cancel it away. And the fact that you cannot cancel it away means that it has to be 0, right? That you're dividing by 0. So that means the dot product has to be 0. So I will leave this details for you. It's almost the same kind of argument. It's a nice argument. You should be able to basically derive it using the same kind of steps. And now let's put the two these two propositions together and explain how you find orthogonal diagonalization. So with proposition 1 and proposition 2, we can justify the spectral theorem in the special case when the eigenvalues are distinct. So I want to give you a justification of the spectral theorem, and so that's going to be the special case. So basically, we have a symmetric matrix, A, and let's label its eigenvalues from lambda 1 to lambda n. Lambda 1 to lambda n. And our special assumption will be that the eigenvalues are all different. So they all have multiplicity 1. And it's very easy to justify the spectral theorem. So label its eigenvalues. By the way, the eigenvalues must be real. That's the nice thing. So the eigenvalues are automatically real. That's proposition 1. So we know the eigenvalues must be real. And then you find the eigenvectors. You find the eigenvectors. You find your eigenvectors, x1, x2, xn. You find the eigenvectors. And these eigenvectors are automatically pairwise orthogonal. So this is proposition 2. What does that mean? That means if you do xi and you take the dot product with xj, you get that it's 0 if I and j are different. Okay, so you form the matrix. So now you can form. Now let me just make this comment. The next step is to renormalize the eigenvectors so they have unit length. In other words, you replace xi by the vector divided by its length. You can always do that. Just any multiple of an eigenvector is still an eigenvector. We did mention that before. You can always take an eigenvector and multiply it by a non-zero number and get another eigenvector. There's more than one eigenvector. So you can always renormalize the eigenvectors. And now if you form the following matrix, and now if you form the matrix of normalized eigenvectors, so in other words, you form this matrix where you just take the eigenvectors and you arrange them into a matrix, just like you do in ordinary diagonalization. Then the matrix is an orthogonal matrix. Since the columns of this matrix are pairwise orthogonal, and the length of each column is of unit length. If you go back to your notes last week when we were discussing orthogonal matrices, we said how do you check if a matrix is orthogonal without actually finding its inverse? Because the hard way to check if a matrix is orthogonal is to calculate the inverse of the matrix and then see if that's the same thing as the transpose. Now, the easier way of checking if a matrix is orthogonal is you take the columns of the matrix, or you can also do this with the rows as well. It also works with the rows. But in this case, let's do it with the columns. You take the columns of the matrix, and you take the dot product between any two columns. If the dot product between any two columns is 0, then you have an orthogonal matrix. And then you also have to check if the length of each column of the matrix is 1. So that's how you check if you have an orthogonal matrix. And that's the reason why this works. because proposition 1 says the eigenvalues are distinct. I'm sorry, proposition 1 says the eigenvalues are all real, so you know you'll only have real eigenvalues. And then secondly, assuming that they're all different, if you find the eigenvectors, then the eigenvectors are automatically perpendicular, because if you have two vectors, if you have two eigenvectors coming from different eigenvalues, then they automatically are perpendicular. So that's the reason why it works. Now, it also works even if you have repeated eigenvalues, but that's a more difficult argument to make, and we're not going to have time to discuss it. So I just at least figured we might talk about the special case so that you at least know about the special case. So now that we understand this, we can do an example, right? So A is equal to what? A is equal to the orthogonal matrix times the diagonal matrix times the inverse, but because O is an orthogonal matrix, it could therefore be written like this, where D, as before, just like an ordinary diagonalization, that's just going to be the matrix of eigenvalues. So that's the reason why that works. And now that we understand this, let's do an example that illustrates this. And you're going to see the actual procedure is rather quite simple. So the majority of this lecture was just discussing the theory behind these symmetric matrices and the nice properties that they have. So you should be familiar with that. But let's actually do a calculation, and you get to see that it's almost the same thing as ordinary diagonalization, except we have to renormalize our vectors so they have unit length. So let's look at this example. So I'll do a 3x3 example. So you're going to have a matrix here. So your matrix here would be 3, -6, 0, -6, 0, 6, 0, 6, -3. You will notice this is a symmetric matrix because if you go down the diagonal, you have symmetry across. So you can fold this matrix in half symmetrically down the diagonal. So that is a symmetric matrix. And the problem here is find the, maybe I should not say the, maybe I should find an, because just like diagonalization, there's more than one way to do it. Find an orthogonal diagonalization for this matrix. So what we want to do is we want to take our matrix A and we want to write it as some orthogonal matrix times a diagonal matrix times the transpose of an orthogonal matrix. That's the way we want to write it. So how does one do that? Well, just like, so the steps here are almost the same. The method is almost the same as with basic diagonalization. We first calculate the eigenvalues, right? That's the first thing that we do. So you have to find the eigenvalues of this matrix. Let me find that for you. Again, you can do this by hand, and I really would suggest that you do these calculations by hand in the beginning, so you know how to do it yourself, because I am expecting that the department final exam will probably make you solve all problems by hand. And you do not want to end up in a situation where you're overly reliant on a calculator. The good news is that every calculation in linear algebra is basically row reduction. So as long as you know how to row reduce, you can pretty much do any calculation you want. So here are the eigenvalues. Okay, those are the eigenvalues. And these are just, this is a possible basis for the eigenspaces. Okay, so you have 3 eigenvalues of this matrix. Again, I really would recommend that you actually find this yourself. It's a good idea to work this out on your own. Once you can consistently do this with a high success rate, then you can start relying on calculators. So you would find it. So the eigenvalues are, here we have 3 distinct eigenvalues. So we have lambda 1, let's write it -9, lambda 2 is 0, and lambda 3 is 9. And then afterwards, so after we find the eigenvalues, we then compute the eigenspaces. Find the eigenspaces first. Now you find the eigenspaces first because after you find the eigenspaces, you choose a particular vector from the eigenspace. But there's lots of vectors you can choose from the eigenspace. So you find the eigenspaces. So here you're going to have, so the eigenspace for -9 would be, and I'm getting this directly from Mathematica. Of course, this is just row reduction if you do it yourself by hand, which we're not doing to save time. But like, for example, if you look at it over here that says -9, if you look at V1, this is giving you a vector. So that is one possible basis in the eigenspace. The actual eigenspace consists of infinitely many vectors. That's just one such instance. So the eigenspace is going to look like this. So by definition, these are the vectors. In this case, it's in R3 because we're in three-dimensional space that have the property that AX is equal to -9x. And if you write it out, if you solve that, you would get that it's -1, 2, 2. You would get that. And then you would write S, where S is just a real number. And then you find the eigenspace for 0. If you work that one out, that would give you that it's S212, where S is just again, any real number. And then you find the eigenspace for 9, and that would be S times this one would be -2, 2, 1, like that. That's what you would get. And then you can pick any multiple you want. You could make S be equal to 1. You could make S be equal to -1. You could make S be equal to 2, anything you want, but you're going to pick the multiple in such a way so the vector comes out to be normalized. You want this to be a normalized vector. So you really have to find the length of the vector. So you're going to pick S in such a way so the correct multiples, the multiples will be chosen in such a way so that the eigenvectors are normalized to be of unit length. So our first eigenvector we will pick, it would be, so let's find the length of this. So 2 squared plus 2 squared. That's 4 plus 1 squared. That's 5. So you have to divide it by the square root of 5. So that would be a -1 over the square root of 5. This would be -2 over the square root of 5. This would be 2 over the square root of 5. Because as you can see, this is just a multiple. That's just a multiple of this one. The multiple for S that you're picking is 1 over the square root of 5. If you want, you can also pick the negative of that number as well. That also works. And then you can pick x2 to be, so for x2, it's up to you how to do it. So you can do the same thing. It's going to be the square root of 5. So you would write 2 over the square root of 5, 1 over the square root of 5, and then 2 over the square root of 5. And then x3 would be, so this would be -2 over the square root of 5, 2 over the square root of 5, 1 over the square root of 5, like that. Okay, so you would write it like this. And then the way you form your orthogonal matrix is you just arrange these into a matrix. You take these eigenvectors and you just arrange them into a matrix. So, okay, so what we're saying is this. We're saying that our matrix A is equal to O transpose, O D O transpose. So if we actually write it out, our matrix is, so our matrix was 3, 6, 3, negative 6, 0, negative 6, 0, 6, 0, 6, negative 3. Okay, and then that would be equal to O. So the way you find O is you just arrange these vectors into a matrix. You can do them in any order you want. The important thing is whatever order you pick, you then have to be consistent with the same order for the eigenvalue. So if you decide to do it 1, 2, 3, then the eigenvalues have to be chosen as lambda 1, lambda 2, lambda 3. If you decide to write it backwards, you can write it backwards. But when you form the diagonal matrix, the eigenvalues will also have to be written in the same order. So you just have to be consistent in whatever order you pick. So it'll be negative 1 over the square root of 5, negative 2 over the square root of 5, 2 over the square root of 5, and then you would have 2 over the square root of 5, 1 over the square root of 5, 2 over the square root of 5, and then you have negative 2 over the square root of 5, 2 over the square root of 5, 1 over the square root of 5. So that would be O. Your diagonal matrix would be the eigenvalues in the order in which they appear. So our eigenvalues are lambda 1, lambda 2, lambda 3. So it's negative 9, 0, 9. So that would be negative 9, 0, 9. And when you actually write it out, it's going to look like this. That's your diagonal matrix. These are the eigenvalues arranged on the diagonal. And then you need the inverse of the matrix. Well, the good news is this is an orthogonal matrix. Its inverse is very easy to find. You just take the transpose of this, or if you prefer, you just arrange these as rows instead. So that would be minus 1 over the square root of 5, negative 2 over the square root of 5, 2 over the square root of 5, and then you would have 2 over the square root of 5, 1 over the square root of 5, 2 over the square root of 5, and then you have negative 2 over the square root of 5, 2 over the square root of 5, 1 over the square root of 5. So there you go. That's the way you factor this. And you can check. I mean, if you really want to do this, you can check that if you were to multiply this mess, you would get that. And that would be the way to do it. Let me just make a comment over here. Because this matrix, so since this matrix is orthogonal, its determinant is equal to plus or minus 1. So if you really want to have a special orthogonal matrix, which is another way of saying a rotation matrix. That's what a special orthogonal matrix is. A special orthogonal matrix is a rotation. So if you want to have a special orthogonal matrix, then you must have determinant equal to plus 1. And to arrange for that, you can simply negate one of the eigenvectors. So that's something you can do. If you negate a row or column in a matrix, then the determinant changes by a -1 sign. So if the sign is incorrect, then that's what you do. Now, I have no idea what the determinant of this is because I did not calculate it. But if you put this into a calculator to find what the determinant of this matrix is, if it comes out to be -1, and let's suppose you want your orthogonal matrix to be a special orthogonal matrix, so you want it to have determinant be positive, then what you would have to do is you can recall what we said. You can pick any multiple of S as long as it has unit length. So what you can do is you can just negate the first one. So what you can do is you can then, what you will do is you simply, if it's not an orthogonal matrix, if it's not special orthogonal matrix, you would just negate the vector. You would just put a negative sign over here. And what's going to happen is these will get negated over here, and then they get negated over here. So this will be plus, plus, minus. And then you achieved, and this way you have achieved a orthogonal diagonalization where you specifically use a rotation matrix to do that. So that's what you would do. So if you, for whatever reason, want to diagonalize in that way, then that's the simple fix. And it's up to you how you want to do it. You do not have to put it into the first column. You can put it into the middle column or the third column. In fact, you can actually put a minus sign on all three columns because then that will change the determinant by 3 signs. So there's lots of ways to do it. But the important thing is that it could be done. That's like the important thing here, is that it could be done. And I know that when you see this, like when you look at this, it looks like this side is simpler. Like you say, well, this looks a lot simpler than this mess. And when you're doing calculations, the right-hand side is actually a lot simpler. Like for instance, if you want to take like the 10th power of this, that's not easy to do. But taking the 10th power of that is very easy. Or there's other things, there's other convenient calculations that make this a lot simpler. Like for example, if you want to find the determinant of this, that's not immediate. You have to figure out how you multiply these out. But taking the determinant of this mess is very simple because we know that this determinant is either plus or minus 1. We know that determinant is either plus or minus 1. And if this is -1, that's -1, so they cancel away. And then the one in the middle, it's a diagonal matrix. So to find its determinant, you just have to multiply down the diagonal. So as you can see, that when a matrix is written in this diagonalized form, it's very easy to actually do calculations with the matrix that would otherwise be more difficult to do directly. So that's actually what I wanted to say about today. I mean, I just wanted to show you how this actually works, how you factorize it in such a way, and the reason why it works for linear maps as well. It's very similar reason as before. If you have a linear mapping which is symmetric, which means that, for example, the linear mapping is given as AX, where A is symmetric, then what you would do is, because the way you find the eigenvalues of a linear map just comes down to finding the eigenvalues of this matrix. So you would find the eigenvalues of the matrix, and after you find the eigenvalues of the matrix, you can then find the eigenvectors of the matrix. So after you find the eigenvectors, that will give you a basis. And the reason why the basis, if these are normalized eigenvectors, this basis is automatically orthogonal because of the earlier of proposition 2 that we said. Proposition 2 says that each of these vectors are pairwise orthogonal. So you're getting a basis. You're getting a basis for this linear map, so that if you were to calculate the matrix with respect to that linear map, you get the eigenvalues, so they become diagonal, and the eigenvectors, they're going to be pairwise orthogonal because that's proposition 2, because they're eigenvectors of that matrix, and since the matrix is symmetric, it means that they're automatically perpendicular. Now, the last thing I wanted to just make a comment about is if you have repeated eigenvectors, let me just finish with this. If you have a symmetric matrix, the eigenvalues are automatically real. but they could be repeated. The spectral theorem is still true, but more work is required to get the orthogonal diagonalization. So you will not be required to know this because it's just more computational. It's just more computational work. Just to show you what I mean, let me just show you the complications that arise if you try to do it. So if we go back to this example that we looked at before, 0, 1, 1, 1, 0, 1, 1, 1, 0. We looked at this matrix before. So this is a symmetric matrix. You can see it's a symmetric matrix. And these are the eigenvalues. But the problem is because these two eigenvalues, like, okay, so look at lambda 2 and look at lambda 1. Lambda 2 and lambda 1. So the eigenvalue 1, 1, 1, and the other one, lambda 2, negative 1, 0, 1, these two are automatically perpendicular. If you take the dot product between these two, you get negative 1 plus 0 plus 1. So the dot product between V1 and V2 is going to be 0 because these are two eigenvalues. These are two different eigenvalues. In the same way, lambda 1 and lambda 3 are different eigenvalues. So that would mean that V1 and V3 are automatically perpendicular, which you can check. If you take the dot product, you have 1 multiplied by 0, which is going to be 0. And then you have 1 multiplied by negative 1 and 1 multiplied by 1. So you have 1 plus negative 1, which is 0. So V1 and V3 are perpendicular. But lambda 2 and lambda 3 are the same eigenvalue. You have a repeated eigenvalue. So V2 and V3, in this case, they happen to be perpendicular. So in this case, they're perpendicular. But sometimes, so I guess this is not the best example because the way it was done in Mathematica, it actually produced for you two vectors that are perpendicular. But I'm just saying, in general, if you had a 3 by 3 symmetric matrix, it could happen that V2 and V3 are not actually perpendicular. Like in this case, they are, but no, actually they're not. No, they're, sorry about that. No, they're actually not in this case. So this is an example of that. Because if you take the dot product between V2 and V3, you have 1 multiplied by 0, you have 0 multiplied by 1, but then you have negative 1 multiplied by negative 1. So the dot product between V2 and V3 is 1. It's not, you can see they're not perpendicular. And the reason why that's not contradicting our proposition is because you're choosing two eigenvectors from the same eigenvalue. And if you're choosing two eigenvectors from the same eigenvalue, they're not guaranteed to be perpendicular. You have to do something else. You have to do something else. So there's an algorithm of how you can take these two eigenvectors and how you can transform them into ones that are perpendicular. So if you're interested, you can look this up in your book. If you're interested to look at this, there's something called the Gram-Schmidt algorithm. And what it says is that if you have a basis of eigenvectors in the same eigenspace, okay, so what we're saying is you have an eigenspace and you found its basis. So you have like S1, X1 plus S2, X2. So you found a basis in the eigenspace, okay? You cannot necessarily just choose them and they become perpendicular. There is a way of choosing it. There's an algorithm in how you can choose. There is a procedure of how to appropriately choose the S's, the S coefficients, so that the chosen eigenvectors from the eigenspace come out orthogonal. And if you're interested, you can look it up in the book. They talk about that. You're not going to be responsible for this because it's just more tedious computational work. In practice, you just have a computer that does it for you, because I think asking a question like that on the exam would just be way too tedious, because finding the orthogonal decomposition is already tedious enough. And if you have repeated eigenvectors, then you have to do even more work to make sure that you're choosing the coefficients in such a way that they come out to be perpendicular.